Alright, let's talk about composition series. Now, in Jacobson, he actually talks about lambda groups, and that's something that I didn't quite learn about when I learned this topic in class. And just from briefly looking through it, it looks like there isn't really much else to lambda groups. Like, typically the standard thing is to just talk about like a group having a composition series rather than like a lambda group, and I think the there's not really much more formalism to it. There's not many more things you have to check. It just makes it a little more general, and you don't have to put a lot of work in. And generally, the rule of thumb, especially in algebra, is if you can get a lot more if you can get a much more general result without a lot of work, do it, because that's the whole point. But I mean, in this scenario, I haven't worked through how you would do this problem for general lambda groups, and my impression is that the proof is not much, or it wouldn't be much more difficult, because all the things like Schreier refinement and Jordan Holder, all those things I'm pretty sure still hold for lambda groups, and so there might just be one or two extra little details you have to add in there. So I don't think I'm leaving a lot out of this problem by not including that. And even if it happens to be like a lot of details that I happen to be leaving out, then at least we have a solution for the case of groups rather than general lambda groups. So anyways, let 1 denote the composition series G is equal to G0, which contains a whole, we have the string and ends with GM, which is equal to E. And so this is the composite, because we're assuming that G is a lambda group we're assuming that G is a group with composition series. And so this is we're going to use 1 to denote such a composition series which it contains, and that'll be what this is. And 2, and let 2 denote the normal tower or filtration or whatever you want to call it. I'm pretty sure it's called normal towers in Jacobson, and I mean it's the most intuitive in my opinion because it has the word normal in it, and that's one of the main ingredients of a normal tower is that it's all things are normal. The other thing being that it's a tower of them. So anyways, so we have these two normal towers. The first one happens to be a composition series. That this is a normal tower. So we're given that, this is H. All right. Yeah, this should be H. So H is normal in G by assumption, and obviously E is normal in H because, I mean, it's trivial. It's normal in everything. Okay, so let's see here. So now, by the Schreier refinement theorem, I can abbreviate that so that I don't have to actually know how to spell the word Schreier. It's an E-I-E-R at the end, which is weird. Anyways, there are refinements 3 of 1 and 4 of 2 such that 3 and 4 are equivalent. I don't like having to include all these others, like look, we already have 4 different normal towers, and we're actually going to end up with a 5th one. But I mean, this is what you have to do, and this is why I actually denoted this original composition series by 1. It's because, like, normally you could just use symbols or something like a star, and then you'd use star star. Then we'd have star 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 and star 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 star, and I really don't like that. I don't like this either, but we gotta do something, and this is the least painful. Okay, so since 1 is a composition series, all graded pieces of 3 are either simple or trivial, because all graded pieces of 1 are simple, and in particular they're non-trivial. And so if you were to add more, if you were to refine that at all, you would just be adding in you'd be potentially adding in trivial graded pieces. So thus all graded pieces of 4 are simple or trivial. And that's because 4 and 3 are equivalent. And so if we know something about all graded pieces, if all the graded pieces of 3 satisfy this property, then the same thing has to hold for the graded pieces of 4, because they're the same up to isomorphism and reordering. Simple or trivial. Okay, so now we will obtain a proper normal series, which we will denote by 5 by, well, normal series 5 from 4 by, for each graded piece of 4, discarding one of the one of the 2 subgroups of G which is involved in that graded piece. Because what's going to happen is, well, wait, here, let me finish the sentence. Except that we do not discard E, K, or G. Here again, I don't know why in my notes I used K, but, yeah, that's supposed to be H, so I might mess that up later on in this problem. I might write K instead of H, and if I do that, I apologize. Hopefully I will catch it. So, oh man, I use K quite a bit in this problem. Oh well. Hopefully I catch it. So basically what's going on here is that we've got so we're taking this normal tower 4, and we're discarding things to make it proper. Basically, so what we're going to do is we're going to go through all of the graded pieces, and some of those graded pieces might be trivial. Now, any of these graded pieces is going to be like a quotient of 2 subgroups, and those subgroups will be two subgroups that appear next to each other in the normal tower. So one of the two subgroups will be normal in the other one. And so once you get to such a graded piece, you're going to have to remove one of these subgroups from the normal tower, either the top one or the bottom one. And in doing this, once you throw it out, we're still going to be left with a we're still going to be left with a normal tower. And that's because if the graded piece is trivial, then yeah, everything will still be fine. And let's see here, the only things we have to watch out for is are we sure that we can make this so that we don't throw out E, H, or G? Well, the only way that we could possibly throw one of them out is if we are in a scenario where we have a graded piece which is formed by the quotient of any two of these. And so let's see here, what are the possible scenarios? It could be the graded piece could be G mod E, but G mod E, that wouldn't make sense. That wouldn't happen because then H would not be a part of this normal tower, because we'd go straight from G down to E. And so that's out. So then the only really other ones we have to consider is, first of all, there's what if we have H mod E? Well, H is a non-trivial normal subgroup of G, and so H mod E, well, that's just going to be H, and that since that's non-trivial, this is not a trivial graded piece, so we won't throw anything out from there. What else could happen? We could have G mod H. Now, is there any issues there? Yeah, I mean, H isn't a non-trivial normal subgroup, and so it can't be that H is equal to G, or else this problem just doesn't make sense. So that's not an issue either. So we're never going to be, that means, therefore, that we're never going to be in a situation where we cannot, we will never be in a situation, well, okay, let's phrase it affirmatively. Given any trivial graded piece, we can always discard one of the subgroups involved in that quotient without discarding E, H, or G. And when we do this, what's going to happen? Then 5. So now we've created 5 by throwing these out, and so 5 is a proper normal tower. Was I saying normal series? I think normal series might be another word that's used for this. I don't know. Things are sloshing around in my head right now, definition wise, so I don't quite remember. But anyways, 5 is a proper normal tower. 5 is a proper normal tower containing H such that every graded piece is simple and hence 5 is a composition series. Oh, that's right, composition series. Well, normal series, whatever. Composition series containing H. So there we go. That completes the first part of the proof, that we do have a composition series which contains this particular non-trivial normal subgroup H of G. So what do we want next? We next want composition series for H and for G mod H. Let 5 be given by And I'm going to rewrite I'm still going to use these G's because, you know, we really never used them. But yeah, it's going to be, we're going to go from G0 to Gn. Gn will be E, G0 will be G, and then Gi will be equal to H. No, yeah. Will it be equal or equivalent, isomorphic? No, it's going to be equal because, yeah, the whole isomorphic case, that's why we had to throw out, if we had it isomorphic, that would be true. That would be an issue. Basically, the way that we threw out these, not the way that we threw out the trivial graded pieces allowed us to get one of them to be exactly H, and I'm pretty sure that had we just thrown them out randomly, then we would have still had a subgroup that would be isomorphic to H, but it wouldn't necessarily be completely equal to H. But anyways, we don't need to worry about that because we have H explicitly in this normal series, in this composition series. So clearly, the K's, H equals Gi, going down to Gn. I don't know why my why I learned to include like this Gn at the end and write that it's equal to E. Maybe it's just so that you can see explicitly that we have this n here that helps you see the order of, or the number of elements in this normal tower. But whatever. It's if you don't like it, it's not too big of a burden to have to put up with. So clearly this is a composition series for H, because we basically just start at H and just go down from there. But where we are going to run into issues is for G mod H, because it's not necessarily obvious that if we just mod everything out by H, then we're going to get a composition series. So, but we're going to fix that. As for G mod H, first note that if Gi contains the normal subgroup Gi plus 1, this implies that Gi mod H normally contains Gi plus 1 mod H. Because if Gi normally contains Gi plus 1, then GHG inverse is in Gi plus 1 for all H in Gi plus 1, and for all G in Gi, this is just what being normal means. And H being normal in G implies that H commutes with all elements of G. And so what? And so we have GH, and I've been doing a decent job of not mixing up my K's and my H's. But the only unfortunate thing is here that I used little h in these computations, because when I wrote this up, I was using capital K instead of capital H. But this isn't, so little h is not necessarily an element of capital H, but if you keep that in mind, then that's fine. So then what's this? What we can get here is we move all these, we can basically commute these h's past the other elements and just end up with GHG G inverse, and then we'd have H cube over here. But, I mean, H is a subgroup, so H cube is just H. And so this is, because, let's see here, GHG inverse is in GI plus 1. This is going to be in GI plus 1H. This is for all H in GI plus 1 and G in GI. And thus, GI mod H normally it contains as a normal subgroup GI plus 1 mod H. So then, oh, that is farther than I wanted to go. Oh. So then G mod K equals G0 mod K, which contains ... which contains G... Let's see here. I'm just gonna... the K's. Okay, so G mod H equals G0H contains... And this is... I'm just gonna end with H mod H, which is E. Not gonna include that element, other thing there. Which we will call 6, so we actually have 6 of them, is a normal series for G mod H. Now, and this is kind of a key step that we're going to use, a key fact, and this really this is really an important fact. So by the group isomorphism theorems, I forget which one, I'm not going to state it explicitly, but what it says is that the K's, this thing is isomorphic to GI mod GI plus 1. What is this? Is this a lattice or the tower? Might be the lattice. Whatever it is. Basically what this is you kind of... Since H is normal in G, you can, like, just sort of cancel it out. But anyways, this is like a really important fact. And it's really necessary in this part. So why is that useful? And each GI mod GI plus 1 is a graded piece of 5 and thus is simple. And hence 6 is a composition series for G mod H. And so there we go. We had to do a little work at the beginning, to just using Schreier refinement and just kind of playing around with our normal series a little bit in order to get it and get the normal series that we wanted, i.e. to get the composition series. And then let's see here, from that we got one of the desired composition series for free, and the other one we had to work a little bit. We had to prove something about how being a normal subgroup is maintained under modding out by a normal subgroup. Well, I mean, just read it. You'll see what I mean, because that was not a very well explained statement. And then at the end we had to use an isomorphism theorem. And so that gave us a composition series for G mod H. And so there we go. We are now done with the proof.